So after looking at concepts like state of stress at a point and Cauchy stress formula, let us discuss now on this topic principal stresses. Now we know that from our elementary mechanics of solid knowledge that if a bar, 1D bar is subjected to say point load P, which is fixed at one end. Now in this case, since this is a 1D bar, assumed 1D bar which is subjected to only point load in one direction, we know that the principal planes will be exactly perpendicular to this applied load. Now similarly, in case suppose say if we have a biaxial element which is subjected to stresses in x and y direction, and then similarly it is also subjected to say shear stresses. In this case, since this is a 2D case, there will be two principal plane which will be perpendicular to each other, and then the magnitude of this principal I mean the magnitude of the principal stresses on this principal plane is given by sigma 1 comma 2 equal to root of sigma equal to sigma x plus sigma y by 2 and so on, which we are well aware of. So to understand the principal stresses in a three-dimensional case, we will consider a same general body which is subjected to different types of forces, and then our interest lies here at this point P. We are trying to figure out what is happening at this P, what is the state of stress at this P. If we know the stresses on a three mutually perpendicular plane, then how to find the stress on an arbitrary plane. This is what we have been discussing till now. So in this topic what we'll try to do is we'll basically try to answer all these questions. If not all three, then at least these two questions we will try to answer in this session. Now the first question tells us that, it asks us, are there any planes passing through a given point on which resultant stresses are wholly normal? Right, so this is what we will try to answer in this topic, and then also we will try to see what is the plane on which the normal stress is maximum and what is its magnitude. So these two questions we will definitely answer in this session. All right, so to understand this, we had seen that if I just take the cut section of this bottom part, then we know that there will be one resultant stress vector at this point P, right? At this point P, we will have one resultant stress vector. And then we had seen that this resultant stress vector can be split along the normal and along the plane. And when we split this resultant stress vector along the normal, we get normal stress, and then along the plane it will be called as shear stress. Now this will be the case on most of the planes, but we are not interested in this in this kind of ordinary planes, but we are interested in a plane on which there will be no shear stress components. All right, that means the resultant vector will pass through this normal itself, and then the stresses which are acting will be wholly normal on this plane. So basically we are trying to find which will be the planes, or which are those planes in this body for a given loading condition, for a given axis, for a given frame of reference, which are the planes in this body on which there will be no shear stress component, and all the stresses which are acting are only in normal direction, because these are the kind of planes on which there are no shear stresses and only normal stress acts. These type of planes are called as principal planes. All right, so principal planes are basically planes on which shear stresses are absolutely zero, there are no shear stress, and the stresses which are acting are only in normal direction. So that means basically there are only normal stresses which acts on the principal plane. So we are interested to find there will be how many such kind of planes in a given three-dimensional body for a given loading condition. So just to give you a brief idea initially, along with this plane there will be one more plane of such kind which will be perpendicular to this plane, and there will be third plane which will be perpendicular to both this plane. In other words, principal planes are the planes which will be mutually perpendicular to each other. All right, so if this is our first plane, right, then its outward normal will be in this direction. It will be in this direction of this plane, of first principal plane. Then suppose say the second principal plane which is perpendicular to this plane, let us consider it to be this. this plane which is in yellow, right, whose outward normal will be now in this direction, whose outward normal will be in this direction. And this, and let me remind you that this is our plane, right, this is our point P which we have considered, which is under study. And then similarly there will be one more plane which will be perpendicular to these first two planes. So these three planes are basically, all three planes are mutually perpendicular to each other. So this outward normal will be in this direction, right? So we see that since these three principal planes will be perpendicular to each other, even the outward normals has to be perpendicular to each other, which can be seen clearly in this figure. So basically now in this section we'll try to find how to locate these principal planes on which there are no shear stresses, and then we'll also see how to calculate the magnitude of the principal stresses which will act on these principal planes, on these three mutually perpendicular principal planes. So this is what we'll be studying in this session. So what we'll do is we'll assume that there is this plane whose whose outward normal is n, and therefore its direction cosines with respect to x, y and z direction will be nx, ny and nz. And we'll assume that the stress which is acting on this plane is wholly normal, and there are no shear stress, or there is no shear stress on this plane. So, and then this sigma, we can call it as a normal stress or normal stress vector which is acting on this plane. So basically what will happen here is the resultant stress vector has to pass through this normal itself, because there is no shear stress as such. So normal stress vector, or I mean to say the resultant stress vector Tn can be easily given as sigma times n, right? And its stress vectors, and the component of this stress vector Tx will be nothing but sigma times nx, which tells us that Tnx, that is Tnx, which will be in x direction, it is nothing but the projection of this sigma on x-axis, and the projection of the sigma on x-axis can be given as cos of that angle, and in terms of direction cosine it is written as nx. So Tx will be sigma times nx. Similarly, T and y will be nothing but sigma times ny, and T and z will be sigma times nz. So let me write this as our equation 1. And let me again remind you that this is applicable only for this special kind of planes which are called as principal planes. But if we had to consider any random arbitrary plane, then the stress vectors on that plane can be given by our Cauchy stress formula, which we had derived in our previous sessions, which is given by this. Right, this is the Cauchy stress formula which helps us to find the stress vector on any arbitrary plane, right? And suppose say if that arbitrary plane is also the outward normal of that arbitrary plane is also n, then we can denote this n, right? So here what we will do is, let me consider this as our equation number 2. I'll consider this as our equation number 2, our Cauchy stress formula. Then from equation 1, whatever we have got for Tx, Ty, Tz can be substituted here. And then finally we can write this as, in place of T and X, I can very well write this as sigma nx for this special planes. And this I can write it as sigma ny, and this can be written as sigma nz. Now if I just readjust this term, if I take this term on the left hand side, I should get this as sigma x minus sigma, right? Because I'm taking this on the left hand side, I'll get this as sigma x minus sigma times nx, because this is a direction cosine which is common for both sigma x as well as sigma. Similarly, in this second equation, I'll get this as sigma y minus sigma and sigma z minus sigma. Let me write this as equation number 3. So from here on, what we are basically interested is in finding this direction cosines nx, ny, nz. And then what are these direction cosines nx, ny, nz? These are nothing but the direction cosine of this principal plane, right? Or any of these principal planes. So basically here our interest is to find this direction cosines nx, ny and nz. This equation here, equation number 3, is nothing but, if you observe this equation carefully, this equation is nothing but it is a set of homogeneous equation, right? Because on the right hand side all the terms are 0, so this is a set of homogeneous equation. I can write this, I can, if I take one simple example, I can have a homogeneous equation of this kind, right? And there can be, say, x plus 2y plus 5z equal to 0, and then say 2x plus 3y plus 4z equal to 0. All right, so even this is an example of set of homogeneous equation. Now the one of the solution for this homogeneous equation is, by straight away if we substitute x equal to y equal to z equal to 0, if I substitute these values here, if I substitute x as 0, y as 0, z as 0, it will still satisfy all these three equations. But then these kind of solutions are called as trivial solution. The reason is, although it satisfies this equation, but it is not giving us any valuable information regarding this equation. Then what is the other way to, in order to determine a non-trivial solution? In that case, what we can do is, we can just take the determinant of all these coefficients like 3, 4, 7, 1, 2, 5, 2, 3, 4, and if we equate it to 0, in that case we can find a solution which will be of much importance, or which will be very much useful later on. Fine. So same thing has been, the same approach we will use it here in order to find what is nx, ny and nz, or what are the values of this direction cosine. What we can do is, we can force this coefficients, the determinant of this coefficient to 0. We can force the determinant of these coefficients to 0 in order to obtain in order to get some valuable information regarding this nx, ny, nz. Because if we just go with this trivial solution, we will not get any valuable information. We will not be able to find this direction cosine of this principal plane. So because of that, what we have done is, we have forced this determinant of this coefficient equal to 0. Now further, if I expand this determinant, I will get this kind of equation. All right, I will get a cubic equation, and this cubic equation is in sigma, right? Because here we have sigma cube, here we have sigma square, some terms times sigma square, some terms times sigma minus some constant. All right, I don't think this sigma is there in this equation here. All right, so this is basically what we will get, equal to 0. So this is the equation which we get after expanding this determinant. So we know that since this is a cubic equation in sigma, the solution to this equation will be, the three roots of sigma. There will be three roots of sigma, and I can denote those three roots of sigma very well as sigma 1, sigma 2 and sigma 3. And we can very well show that these will be always a real roots. All right, these roots will be always real, which we may also prove in our next sessions. But for time being, we will consider that this three roots will be real roots. All right, so these roots are real, it will be real, we can prove it. So basically what we have done till now is, we have been able to find what will be the magnitudes of principal stresses, three principal stresses, sigma 1, sigma 2 and sigma 3 on these planes, right? These were our three principal planes, and with this approach, what we have done now is, we have been able to find the values of sigma 1, sigma 2 and sigma 3, which are nothing but our principal stresses. These are principal stresses, and they are in following order. If suppose say sigma 1 is highest among all these three, then we can say sigma 1 is highest among sigma 2, which is again highest among sigma 3. So basically we will follow this order to denote sigma 1, sigma 2 and sigma 3. Whichever value is higher, we will be denoting that value of stress as sigma 1, following by this value sigma 2 and sigma 3. Now we have been able to now find one thing out of one. We have been able to answer one question out of these two questions, that is, what will be the magnitude of the principal stresses, right? So the magnitude of the principal stresses we'll get once we solve this cubic equation. and we will be able to find the magnitude of the three principal stresses, sigma 1, sigma 2 and sigma 3. But now we have not found yet what will be the direction cosines or what will be the orientation of these principal planes, that is nx, ny, nz. So we know that with each sigma we will have three direction cosines. For example, if I take this first plane, so we know that the magnitude of the principal stress on this plane, what we have got is sigma 1. But what will be its direction cosines? What will be nx, ny, nz values, or what will be the cosine angles between this its outward normal and x-axis, y-axis and z-axis? So that is what we will be finding now, right? So similarly, if we consider sigma 2, now this sigma 2 stress, normal stress, will not be on this plane, but it will be on a plane which will be perpendicular to this plane, let us say this yellow plane. So again we have to find then what will be the direction cosines of this plane. Alright, and that can be done very easily by doing what? By once we obtain this value of sigma 1, suppose say sigma 1, what we can do, we can substitute this value of sigma 1 back in this equation. Alright, we can substitute the value of sigma 1 in this equation, and then we can use the constraint which we know on the direction cosine. The constraint which is there on the direction cosine is that the equation of the direction cosine is nx square plus ny square plus nz square will be always equal to 1. So if I use this value of sigma 1 here in place of sigma in any of the two equations, and using the third equation of direction cosine as this, right? So what basically we will be doing is we will be using the value of sigma 1, we'll be using the value of sigma 1 in these equations, in any two equations, in this set of equation number 3, we'll be taking any two equations out of this. We will be substituting the value of sigma 1 here in place of sigma, and then the third equation what we will be using is this. And then once we solve these three equations, we should be able to get nx1, ny1 and nz1, which tells us that these are the direction cosines for sigma 1. For the first principal stress sigma 1, the orientation of its principal plane will be nx1, ny1, nz1, which we will get from this equation. Similarly, if I want to now find the direction cosine of second principal stress, the same thing what we can do now is we will take the value of sigma 2, we will substitute it here in this equation. In place of sigma, we will substitute the value of sigma 2 in any of the two equations. We will take those two equations and then we will use this as our third equation again, and then similarly for the case of sigma 2, we will be able to find nx2, ny2 and nz2, and similarly for sigma 3 we will be able to find nx3, ny3 and nz3. Once we start solving some problems on this will be more clear, but for time being you understand that with each principal stress there will be a principal plane which will be associated with it, and the orientation of that principal planes will be given by nx1, ny1, nz1 for sigma 1, nx2, ny2, nz2 for sigma 2, and nx3, ny3, nz3 for sigma 3. So with each principal stresses we will have a plane. So just to make one statement, what I can write is with each sigma there will be an associated plane, right? We saw that with each sigma there will be one plane, right? With each sigma there will be one plane. This is, suppose if this is for sigma 1, this plane will be for sigma 2, this plane will be, green plane will be for sigma 3. So for with each sigma there will be an associated plane. These planes on which the stress vector is wholly normal are principal planes, and the corresponding stresses are the principal stresses. Okay, so with this we have been able to find the principal stresses as well as the direction of the principal plane or the orientation of the principal plane. Again, just to revise, we got three principal stresses as sigma 1, sigma 2, sigma 3, and associated with these three principal stresses we know that there will be three principal planes whose orientation will be given as nx1, ny1, nz1, nx2, ny2, nz2, and nx3, ny3, and nz3. So now what we'll do is we'll slightly go to a different topic called as stress invariants, and let us try to understand what do you mean by stress invariants. Now if you observe this cubic equation here, if we observe this cubic equation, I can write these terms sigma x, sigma y, and sigma z as, I can write this equation sigma x plus sigma y plus sigma z as I1. Alright, I can denote this term sigma x, sigma y, sigma y, sigma z, sigma x, sigma z minus all these terms, shear stress square terms, as I2. And then finally this term I can denote it as I3. Now these terms will be called as stress invariants. I1, I2 and I3 will be called as stress invariants. So if I substitute these terms here in terms of this stress invariants I1, I2 and I3, I can write this equation as sigma cube, right, minus, in place of this I'll substitute I1, so it will be minus I1 sigma square plus I2 sigma plus I3 equal to 0. Yes, so I can write this cubic equation in terms of stress invariants. And then before actually going into this term stress invariant, before actually trying to understand what do we mean by stress invariants, I'll just show you how to remember this equation. This is very easy to remember. This is sigma x plus sigma y plus sigma z, but I2 can be denoted in terms of matrix form very easily, as I can write this as sigma x tau xy. This will be tau xy sigma y, right? Similarly, plus it will be sigma y sigma z tau yz tau yz, plus this will be sigma x sigma z tau xz tau xz. Fine, we can even write this equation I2 in this form, in this matrix form. And representing I3 is very simple. I can just write our rectangular stress components, that is sigma x sigma y sigma z. This will be tau xy tau xz. This will be tau yz. Similarly, this will be tau xy, tau xz, tau yz. And if I just take the determinant of a rectangular stress component, I will get nothing but this expression again. All right. So basically, this is how we can remember these values of I1, I2, and I3. And once we get the values of I1, I2, I3, I can use this cubic equation to find the three roots of this cubic equation, which will give us the principal stresses sigma 1, sigma 2, and sigma 3. All right. So we have understood how to make use of these stress invariants, but actually what are stress invariants? What do we mean by stress invariants? The stresses is what we know already, but what do we mean by this term invariant? Now the meaning, literal meaning of this word invariant is something which doesn't vary. Now what doesn't vary with respect to some frame of reference? To understand that, let us again consider our same example, that is a body which is subjected to different forces. Our area of interest is this P, right? We are basically trying to find the stresses at this point P. Now whenever we denote this rectangular stress component across a small cube at this P, whenever we try to denote it, it is always with respect to some frame of reference. It is always with respect to some frame of reference. Now in this case, our frame of reference is this Cartesian coordinate x, y, and z, right? Suppose say if I now change this frame of reference. Suppose say for this frame of reference x, y, and z, we had drawn one cube to across this point P, and then this will be our x planes, right? This two will be our this plane, and this plane are our x plane, because its outward normal are in the direction of x. Similarly, these two are y planes and these two are z planes. So on this x, y and z plane, we will get the values of sigma x, sigma y, sigma z, and later on this shear stresses tau xy, tau xz, and so on. But let me tell you that the rectangular stress component which we will obtain here, right, will what kind of rectangular stress components will obtain? We'll obtain the rectangular stress component as sigma x, sigma y, sigma z, then tau xy, tau xz, tau yz, and then similarly this is tau xy, tau xz, and tau yz. Now this rectangular stress component which we'll obtain is valid only for this frame of reference. The moment we change this frame of reference to some other frame of reference, the moment we orient this rectangular, I mean this Cartesian coordinate system. For example, we have now, what we have done is we have rotated our Cartesian coordinate system. This x has gone to now new place, that is x dash. Similarly, y has gone to a new place y dash, and z has gone to a new place z dash. So basically we have rotated our frame of reference by some values, by some angles, but the point is same. All right, the point still is same, the point is same. But now if I want to, for this frame of reference, for my new frame of reference dash, x dash, y dash, z dash, if I want to draw a cube with x dash plane, y dash plane, and z dash plane, that cube will look somewhat like this, because now x dash plane has to be in this direction, so that its outward normal is in the direction of x dash. Similarly, y dash plane has to be in this direction, whose outward normal will be in the direction of y dash, and z dash plane has to be in this direction, whose outward normal will be in the direction of z dash, right? So in this case what will happen is, I will again have some normal stresses at this point on this plane, right? Some normal stresses on y plane, some normal stresses on z plane, then shear stresses, and then in this case I will get the rectangular stress component as what? I'll get it as sigma x dash, sigma y dash, sigma z dash, right? Tau xy dash, tau xz dash, tau yz dash. Similarly, tau xy dash, tau xz dash, tau yz dash. So basically here what will happen is, this sigma x dash will not be equal to our sigma x which was obtained at the same point, but with this frame of reference. The moment we try to change the frame of reference, all these values, all these rectangular stress component values will be different. For this frame of reference we had got these values, but the moment we change the frame of reference, these values will change. Suppose similarly if I rotate it to some other orientation by some other angle, in that case again across this point the stresses which we will obtain on the cube, on that cube, will be different. All right, so from here what we come to know is that as we are changing the frame of reference, these values of sigmas are changing, right? For say for x y z coordinate system, we had the stresses as sigma x, sigma y, sigma z, and then we had tau xy, tau yz, tau zx. But the moment we change this, our frame of reference to x dash, y dash, z dash, we will get some different values of normal stresses. Let us call it as say dash, to denote there is a difference between these two values. All right, similarly now if I take this frame of reference to some other orientation, and in that case again these values will be something different. So from here we come to know that as we change our frame of reference, the values of the stresses will change, but there will be some quantities which will not change even with this, by changing this frame of reference. All right, so I'll write here, but there will be some quantities which will not change even after changing the frame of reference, and those values are called as, stress invariants, and those values are called as stress invariants. So even after changing the frame of reference, there will be some combinations of these stresses which will not change its value. For example, what was our I1? Our I1 was sigma x plus sigma y plus sigma z. So for this frame of reference, our I1 will be what? I1 will be sigma x plus sigma y plus sigma z. But what will be the I1? What will be the value of I1 for this new frame of reference x dash y dash z dash? It will be what? It will be I1 dash will be sigma x dash plus sigma y dash plus sigma z dash. But one will be easily able to observe that I1 will be equal to I1 dash. So this combination of stress, the addition of three normal stress, will not change with different frame of reference. Of course, this individual values will change as we change the frame of reference. The individual stress values will be different, but the certain combination of these values, that is the first combination is sigma x plus sigma y plus sigma z. Now this combination, the combination of these values will not change with different frame of reference. Even if we go for third frame of reference, even then I will have this kind of combination sigma x dash plus sigma y dash plus sigma z dash. Even that will be same as this. Even that will be same as this, right? Even that will be same as this. Now, similarly, there will be two more quantities which will not change as we change the frame of reference, and those other two quantities are nothing but the second and third invariant. So I1 is called as first stress invariant, this I2 is called as second stress invariant, and I3 is called as third stress invariant. So even this combination of stress, suppose if I multiply now sigma x dash and sigma y dash plus sigma y dash sigma z dash, which are the values of the stresses for second type of frame of reference or other frame of reference, then even this combination, if I combine it this way, even this will give us I2 dash, which will be same as I2. So in this case I2 will be equal to I2 dash. All right, so this is why these values are called as stress invariants. So there are so if someone asks you all now what are stress invariants, you can say that the values of stresses in a stress component will change with the different frame of reference, but there will be certain combinations of these stresses which will never change with any different frame of reference, and those combinations of stresses are called as stress invariants. All right, so stress invariant means something which doesn't change with different frame of reference, something which doesn't vary with different frame of reference. So that is why these terms are called as stress invariants. So here I can conclude that I1 will be equal to I1 dash. Similarly, I2 will be equal to I2 dash, and I3 will be equal to I3 dash. Right? And what are I1, I2, I3s? We know that I1, I2, I3s are this. Right? If I just erase this from here, just to be more clear, what are I1, I2, I3s? I1, I2, I3s are this. So these I1, I2, I3s are written in terms of rectangular stress components, right? In terms of this rectangular stress components. If I want to denote this stress invariant in terms of say principal stresses, we know that our principal stresses are sigma 1, sigma 2 and sigma 3. Suppose if I want to denote what are these I1, I2 and I3 in terms of principal stresses, then our I1 can be written as I1 will be equal to sigma 1 plus sigma 2 plus sigma 3. Similarly, I2 will be sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 3, sigma 1. And I3 will be sigma 1, sigma 2, sigma 3. All right, so this is how we can represent the stress invariant in terms of principal stresses, and this is how we can represent stress invariant in terms of rectangular stress components. Just take the note of this units here. The unit of I1 will be what? It will be in terms of megapascals. But what will be the unit of I2? Since we are multiplying here two stress components with each other, it will be in terms of megapascal square or pascal square. But this will be megapascals or pascals. Similarly, the unit of I3 will be megapascals cube. So this is what all I wanted to discuss in this session. All right, just to revise, we have been able to find that there will be three principal stresses in a general three-dimensional body. Those can be represented by sigma 1, sigma 2, sigma 3, and with each of these principal stresses there will be principal planes which will be associated with this, and the direction cosines of those planes can be given as nx1, ny1 and and z1. Similarly, direction cosine of this will be what? nx2, ny2 and nz2. Similarly, the direction cosine of this will be nx3, ny3 and nz3. And then we saw something called as stress invariants, and then we saw that with different frame of reference the values of stresses will change, values of these rectangular stress components will change, but there will be certain combinations of these stresses, values of combinations of these stresses which will not change, and those combinations of the stresses are here. These are the combinations of stresses whose value will not change with different frame of reference, and those combinations are called as stress invariants. And in particular, they are called as first stress invariant, second stress invariant and third stress invariant.